every night. Astronauts in endless flight, chasing stars and chasing light. Black holes hide where we can't see, secrets they will always be. Yet we dream relentlessly in the space where souls roam free. Universal light so fast, moments here they never last. Floating through the starry past, journeying far, we're going fast.
Hey everybody, welcome to the SkyTour live stream. It is me, this guy, the guy in the lower left corner. It's Mark D'Antonio. Nice to see you. Welcome. For a second night in a row of some streaming, we're going to look at the final summer sky. I mean, look at this beautiful supernova remnant. I mean, this is what's called the Eastern Veil. And we're going to kind of go northward from here and circle over the pole and look at a couple of things. And look at some things we've actually never looked at before tonight, and that's actually going to be fun as well. So we're going to look at some really cool star clusters and just take a journey through basically the northern sky and see what's really out there. I mean, there's hundreds of objects out here. I want to say hi to everybody that's here so far, and of course a special hello to Lane, who's here. Hi, Lane. And Lane is with, of course, Daisy and Zoe Amethyst. Daryl is still under the weather and won't be joining us tonight. I want to say hi to Michael Hedrick. I want to say hi to Good Vibes and Wayne Pinkham, my buddy. Marco's with us. Sam S. is with us. And Mr. Django from Belgium. How you doing there, Stephen? And, of course, Roy Batty is with us. Hiya, Roy. Nice to see you. And we haven't had any drones in our view, as Roy's asking. Any drones? I was out, like I said the other day, with Friday night I went out with police down in western Connecticut, where I live, and southwestern Connecticut is where it was. And I went out on a police call with Ben Hansen and a few others to actually see if we could find a drone, because it was a drone call, and we didn't see any. But we saw plenty of airplanes, and it turns out many planes are being mistaken as drones, because now people are looking up in the sky for the first time and see blinky lights. It's almost like this the first time. Anyway, we're starting off tonight with the Eastern Veil, the eastern side of this supernova remnant. It's a big, expansive supernova remnant that is about 1,600 light years away or so, and it's been expanding for about 8,000 years since it first formed. It's several full moons across in the sky. It's pretty large, and it's a combination of many different materials. You can see the different colors, though those do mean something. And what's happening is, as this material is moving outward at high speed, it's colliding with other material that you don't see. And that actually heats the temperature up, sometimes to millions of degrees. And those temperatures, those very, very high temperatures, will cause the hydrogen gas to glow red, and because it's being ionized by this high temperature impact and so forth. And the oxygen out there is being ionized, and it glows sort of a teal blue. We had a problem with our color rendering earlier in the month when we couldn't get the correct colors, and I figured out what the problem was, and I fixed it. And now look at this. We're getting actual to your eye colors as you would see in space if you could see color. You'll notice if you look at this through a telescope, if you had a very large telescope, it might look like this. Okay, it look like it's like black and white. That's because as much light is coming from this, it's still very faint. Now in bigger telescopes, you might see something like that. Notice the little color change. There's a little bit of red here, a little bit of greenish blue, a little teal. And only with a special camera will you get this rich true color value. Really cool. Hey Donald Kunzer, nice to see you. And I think that it's kind of cool that we're doing this right now, because if we look in our view here, let's actually go to our all sky first. Here's the all sky camera view, and if we bring up our constellations, you'll see Cygnus over here, and where we're looking is right here. Okay, so we're actually in the northwestern sky. So Cygnus will be going down below the horizon tonight, as it's then, and then we'll be focusing on this region up here. We're going to be going through here and looking at some objects up here that are really cool. And there's an awful lot of clusters up here to check out. Really, really good stuff. Anyway, so that's where we're going. And this is the summer Milky Way giving way to the winter Milky Way. Orion has already risen. You can see over here, there's the belt stars of Orion. There's Betelgeuse. Okay. Slight distortion in our spherical acrylic cover on our all-sky camera. So it's pretty cool. Renee Cruz. Oh my gosh. You broke your arm? Oh no. What's going on? I want to know who you hit that you broke your arm, because that's what happened, huh? You had to hit somebody, didn't you? Let me know. I just sorry you got a broken arm. That's unfortunate. Okay, there's a satellite going in there. Okay, so this we're gonna save this now. Okay, and save it exactly as seen. All right, and now that's good. So now this one, I was starting this before we started. Look at I got 81 exposures of 25 seconds apiece. I've been letting it sit here for over 30 minutes, acquiring imagery, and the payoff is when you zoom in. Look at this. Look at how clear that is. Normally when we zoom in, we see all kinds of digital noise, but the longer you stack and make an image sandwich, the more that noise is eliminated. So we can actually zoom in until we start to see it, and you get an idea how far in we have to go. All right, look at that. We're in over 500%. You can start to see some of the noise, but you still see some structure. And that's pretty cool. Now, if this was closer to us, then it could actually be that big in our sky and cross our whole sky. Very interesting. All right. Yeah. Hey, Bill Connolly, how are you? Oh. So now let's do it. Hey, Cosmic Flow. Cosmic Flow says, that is cool. Alright, we'll save this one more time with 84. Well, actually, we'll stop on 85, so let it go one more. This complex structure down here. Look at this right here. Let's zoom in on that. I want to show you. It's way at the bottom of our view, but look at this very, very delicate gossamer streamers. These are, several light years long, guys. Okay, thin streamers of gas that's been ionized. And it might be electrical charge that's causing the streamers at all. That's a thought process going right now out there in the world of astrophysics. All right, so we saved it here. We'll save it exactly as seen. Okay. So that is part of the supernova remnant that we're looking at. We're going to just look at the other part, another part of it. It's a very, the other part we're going to look at is a very convoluted part of it. And it's to the right of it over here. But we'll go into our program here, our planetarium. And we're going to center this first and zoom in. And you actually see the entire remnant here. So there's a one we imaged. we have a central part, and then we have a western part. So somewhere inside this circle is the remains, a black hole that may very well be in the middle of all this, that was formed when the star exploded and went supernova. So right now we're going to look at this right here. This location right here is called Pickering's Triangle, right? And we're there right now. We're going to come here. So I'm going to first I'm going to do this. I'm going to do an annotation first of all. Okay, all right, and then we'll say save the image with annotations. So we have a good thing. And then we're going to go and let's go to that star 10316. That is a star. And there it is right there, 103116. We're going to say center in the view. All right. And while that's doing that, okay, you'll see this star, and I'll move to the center. This product is beautiful. We're going to come over here, and now we're going to look for that star. All right. And then we're going to say, okay, it's going to be a Hipparchus star, a Hipparchus catalog, 103116. There it is, and that should be right nearby. There it is. And now what we're going to do is notice where our cursor is. This is where our telescope thinks it's pointing. That's where it's pointing. So we're now going to synchronize and make this go here. All right. And there it goes. Okay, so now our telescope is synchronized, and we're going to just move things like they have to. There we go. All right, and now what we'll do, okay, there we go. And now what we'll do is go to the other section of this that we want to go to, which is right here. We're going to put Pickering's Triangle right there. So we're going to get a little bit of this, a little bit of that. All right. And so we're going to tell the telescope to go to this center position. If we drew an X through here, the center point is where we're going right now. And you'll see the crosshair for STLS move here. All right. So we should see this come through like that. And there we go. Okay. Perfect. And now when we come back, you'll see Pickering's Triangle right here is our object that is in our view. So what we can do is now go in and do a 25-second shot of this. And we should see some material up here and some stuff down here. And that should be pretty cool. So now we're going to live stack that. And you'll see the previous one we did. Well, maybe not, because I already had this up there. Yeah, so it won't be there once you get rid of that. That was the eastern veil we had. And now you will see the central, this is called the central veil, or the middle of that supernova remnant. And remember, this is in 3 dimensions, remember. So that part could be coming toward us, with some of it going away from us. Okay? And the colors don't much matter. They don't tell us whether things are coming toward us or away from us. All right, so this is the top part of Pickering's Triangle, and that. All right, so I want to move that a little more. We're getting there. Okay. Alrighty. Okay, so we're going to move down a little bit. To get more of Pickering's Triangle in here. Move a little bit west. Here we go. Okay, so let's go back to here and do this again. This identification is actually pretty close. You can see NGC 6974 right there, little tiny blob right there. Supernova remnant, another one. Let's see now. So let's come out of here. Let's go in and do a 25-second image of this. Okay, and now we'll get rid of our low light mode and go into our deep sky mode. Hey there, Tim F. Okay, this here is going to clear because that's now going to be up higher. Let's take a look at our image here. So we're out here in Cygnus. There's Deneb. There's the central star, Satyr, and this is Alberio. And then this is the two cross stars here in the cross piece of there. Okay, let's now come out. Yeah, and here you can see Pickering's triangle with that upper part that I was telling you about. This is really just a beautiful beautiful region, and what I'm going to do is pull in the black level. Alright, and that'll darken up the background. And I'll color correct it just to make sure that we have all the detail. Yeah, it looks pretty. And we can pull this in a little bit just to brighten it slightly. Look at all the stars. I mean, it is literally, there's so many stars in this region of the sky. So many. Now coming up in the sky is the whole winter sky. And the winter sky is by far the most beautiful sight that we have shown you in the past. Hey Wayne, thank you. Thank you so much, Wayne Pinkham. That is a fantastic. I appreciate that so much. If anybody else wants to donate, you can go to skytourlive.org and do it there, or you can do the super chats, whatever you like. It's not obligated. You're not obligated in any way, but understand that I don't make any money on this. I don't take any money for this. Outlaid a lot of equipment, I can tell you that. A lot of expense to put all this in. And we have some donations that have actually come in to help us with a second scope. And now we just need to get the second scope into the new observatory location, which is being held for us pending the funds to install it in the building. But I have faith that we'll be able to do that. Thank you again, Wayne. That was very kind of you. Fantastic. Wow. All right, so let's see now. Oh yeah, a satellite just went through. That's okay. Let's color correct, get that sky a little more black, and that'll change the colors, as you can see. So we zoom in, you'll actually see the colors now. Look at the complexity in this part. Now this is the stuff that's coming at us from around the middle of this supernova rim, because from the side it would look like this, it's going outward. And so from the front, it's coming toward us, some is, and some is going away from us, as that central point is straddled by this material in 3 dimensions. So that said, I'm not sure, because I don't know. There's a study that differentiates what part of this is going which direction. I think there must be a study that shows that. And by the way, I think I mentioned Daryl's not here tonight again. He's under the weather. He's okay. He's just feeling a little sick. So tonight will be just me again. But that's okay. It started with just me years ago, so that's nothing I haven't done before. Okay, let's zoom out a little. Okay, on this we're just going to go to maybe 12 exposures and then move on. And after this one, okay, we're going to leave this region and we're going to head over to Satyr, Solder as we will call it sometimes, and we'll take some images here of the Gamma Cygni Nebula. This is an extremely rich region of nebula. It's not square, that's just where the photo stopped. Okay, but there's a lot of intricacy in here that's fun to look at. So we'll take some quick shots over there, and then we'll move north. I'm debating whether we'll stop here at the North American Nebula, because that could take the entire night to image that whole thing. We might, but we'll see. And then, as we come up here, you'll see all these little clusters. We're gonna hit some of those clusters and check them out, because some of these clusters are just beautiful. You know. Hey there, Michael Galea. How are you? Hey, Carbon Star. It's the Borg Cube Nebula. Yes, that's what it looks like, right? Yeah, that's funny. It actually extends all the way into this, and I mean, it's really quite something. Okay, there's 12. We'll save it. Let me first set that. I'll name it. This is going to be the Central Veil. Alright, there we are. Hey, Stuffy. And we'll save it now. Lucky 13. Alright. Okay. So that, again, that's the Central Veil, alright? And so that's coming at us and going away from us, but we don't know which is which by just looking at it here. Okay, let's jump in now to our low light mode again. Because in our low light mode, we'll be able to figure out where we're going next. All right, now let's go here. Before we get here, let's see if there's anything along the way we might want to look at. I don't think so. All right, so we're gonna come down. We're gonna go here. We're gonna go to Satyr. Put Satyr right there. All right, here we go. All right, so we're gonna move now. For those that may or may not know, and some of you probably remember, there's Satyr right there. I'm in Connecticut, and the telescope is 2,600 miles away out in the Arizona desert. I can't tell you enough what kind of challenges we had to overcome to be able to control it from Connecticut like this. Now, we had to have redundant features. We had to have control. We had to have control over power should anything go haywire. And we do. And we're actually improving on that when we go to Benson, which is 200 miles southeast of this location. If we can get our telescope into the Benson Observatory, oh, there goes a Starlink satellite. Ching! It's a dash because we're taking a 1 second exposure, as you can see up there in the corner, 1,000 milliseconds. So in 1 second it travels this far. And so that's why you see it as a streak and not a dot moving through. If I made that a very short exposure, you wouldn't see as many stars, but you'd see the thing moving like it should. Okay. All right. This looks like it might be good. Let's actually, we'll do a 20-second shot of this. 20 seconds is all that's needed. This is a very bright nebula. All right. And it's off and running. So we'll come out of the low light mode and go into our deep sky mode, as we call it. You'll see the previous shot of the Central Veil. Very good. And then we'll clear it, because when I save these, well, guess what? They're going up to the server at skytourlive.org, and within 30 seconds, they're available for you to download and put on your machine and enjoy. Oh yeah, look at that. This is the Gamma Cygni Nebula, and let's actually pull out a little more detail going right out of the chute. Okay, this is the first time I've imaged it with this camera. I haven't imaged it yet with this camera. So we have a beautiful star cluster right here. We have the center of Cygnus the Swan right there. And then we have this beautiful nebula. This is dark dust right in here. This is all dark dust. It's not two separate nebulae. There's just one nebula here. But this is sitting over it, and the nebula is back here. Okay? That's what's interesting. That dark dust is sort of obscuring what's behind it. And that's what this is, little fingers of dark dust. And that becomes clear as we move forward. That'll become a little more clear. Stan from Two Rivers is with us, and Marianne Robb is with us. Hey, Marianne. Hey, Jake. Jake is here. And Jake bought his son a telescope for Christmas. What kind of telescope did he buy, Marianne? As you know, Marianne is one of 3 people that are the starters of our nonprofit organization that is SkyTour Livestream. Tara is the other. Tara's actually coming out to this observatory tomorrow to help us with some maintenance. And she's going to remove a component that has been kind of flaky. And I'm going to replace it, not this trip, but the next trip, which is going to be soon. I'll be replacing it with a second little computer, which is going to control more things in there. And control the main computer. I have a computer going in to control the computer, which is kind of cool. It's sort of a backup system that's going to allow us to turn on and off power whenever we want. Because right now we don't have that ability. We just have a timer. And I don't like having a timer. It takes control out of our hands. And sometimes I want to maintain that control. Look at that. Look how rich this is. This is gorgeous. Wow. So let's zoom in on this dark nebula here so you can see some of the detail in here. Look at this. There's dark tendrils in here. And behind it you can see the nebula that it's hiding. Okay? And again, not voids in the stars. These are just actual dark rifts of dust. Rift, R-I-F-T, rifts of dust. And this stuff is generated by older stars building molecules in their outer atmospheres because they're so big that it's cool enough, still hot by human standards, but cool enough for molecules to form. And those molecules of dust combine with each other. Those little micron-sized particles combine, making bigger and bigger particles into larger and larger molecules, and then they attract other materials which freeze to the surface in the near absolute zero cold of these dark clouds, and you get ice on the surface of these dust grains. This is a frozen refrigerator of life-bearing, not life-bearing, but life-capable chemistry that is held in stasis, effectively, dormant until a star forms, heats it up, melts it all. Next thing you know, that dust and gas, which is mostly hydrogen, forms a star from the hydrogen, and planets form from the dust and all the many chemical slurry of materials that have adhered to the dust in here. That's where we came from. It's pretty cool. James Hyatt's with us. Hey there, hey James, what's up? Nice to see you, stranger. Okay. Yeah, so if I was to name this one, let's see what it will give us for a name. Yeah, it knows the cluster, and it knows these stars, but doesn't know. It doesn't know the. I guess we'll call it Gamma Cygni. We'll set that target name, but it's actually the Gamma Cygni Nebula. So I'll add that to the list here. Yep. Now, if you're wondering where to find these, in last night's stream, I showed you the whole process. I showed the entire screen. I showed you SkyTourLive.org and where to find different things, what the database looked like, how to get to it. So you can either watch that part of it, or you can actually go to SkyTourLive.org and read the instructions as you scroll down to Take Me to Cool Pictures. The area says that, Take Me to Cool Pictures. And that's what you'll get. Let me save this image with the annotation. Okay. So our nebula picture, that particular nebula picture, will have annotation on it and labels. Okay, 16 images here. We'll save it. And save exactly as seen. That's good. That's good for this one. All right. And now we're going to go to another beauty in this region. And that's going to be one of the many clusters that we see here. One of the things that's interesting about these clusters, and I'll show you, is that they all form in places like this. In places like this, the nebulae, they all form there, right? And we'll just check out this one here, because this is an example of one that no longer is associated with a nebula. It's moved out of the nebula or cleared it away with its young stars. All right. Okay. Cygnus is a very rich region. Let's see if we caught the cluster. Oh, we have a planetary nebula there that's very faint. A Hipparchus star. That's interesting. Let's go see that planetary nebula. Oh yeah, you can see it there. Interesting. All right. That's neat. What we're going to do is we're going to do a little deviation, and we're going to move that down to the center. Actually, I should have left that there. Let's put it back. Okay, this is NGC 7048 right here, and we're going to move that to the center in the view. Okay, here's something we've never seen before. We've never seen this before. So we'll move it to the middle. And then we can come out of here. And it's right there. And now what we'll do is we'll do a 20-second exposure, no, 25-second exposure of this guy. First things first, I'm going to move a little to the west. I'm going to jog us a little bit to the west. There we are. Okay. Never seen this one before. Cool. So let's go into our live stack. Okay, get rid of the previous image. And we're 10 seconds or so from the next image. Rocket City Astros with us. Carbon Star says the concept of heat in a low-density environment where you have little conduction has always been fascinating to me. Correct, and that's a very interesting comment, and actually a very good one. Let's talk about that for a minute. When you're looking in space, space is very low density, obviously. Even the most dense dark nebulae, where it's actual material, sometimes the density is 30 atoms per cubic centimeter. In other words, 30 atoms in the size of a sugar cube, as opposed to like 10 to the 20th atoms like in the sugar cube of air. Okay, so very, very low density. However, what happens in space is not so much changes in temperature, but changes in emissivity, that is, radiation being given off, like by a star, or absorbed by something like an asteroid or a planet or a meteor or particles of dust. So things in space only absorb or radiate radiation. You don't think about them in terms of temperature. You think about how much radiation they're emitting or how much radiation they're absorbing. Okay, temperature requires pressure. You may remember the ideal gas law from chemistry. PV equals nRT. N's a constant, R is a constant, T is temperature. P and V are pressure and volume. If you don't have any pressure, you don't have any temperature. You have pressure 0, you have 0 temperature, right? You have no temperature, it's undefined. So you have to consider that temperature doesn't exist in space per se, right? You have volume in space. You can make a volume, a temporary, with an arbitrary volume, but you don't have any pressure in there. So in the rarefied meaning low density regions, you will have few atoms per sugar cube, basically per cubic centimeter, and so you'll have the dust in there able to absorb a certain amount of radiation from nearby stars, and then will radiate it as infrared energy. Okay, now, if you could get inside the dust particle, you could indeed measure a temperature, but the temperature inside the object is going to be affected by the size of the object and how much it can, its thermal mass, how much mass it has to absorb radiation. So it's all about absorption and emission of radiation in space. Okay, it looks like I might want to do a little focus adjustment here. Stars look a little soft. Let's go in. Oh yeah. Okay. So let's clear this and go out here and go back to our one low light mode, and then we will do a focus adjustment. Okay. Okay, sorry, let me get rid of this. Okay. So as you can see, our stars are just a little out of focus. So we're going to change that. This is our focusing section over here. But I'm going to focus our stars now. Make them a little bit better. Alright. So let's go here. And start to focus. So, American Road Warriors here. That's Eric Hartwig from MUFON, Massachusetts, checking in. He's the state director for the Mutual UFO Network there. And he says, shoes on fire. I'm not sure I want to know what that is, Eric. What's going on, Eric? How you doing? And Rocket City says, getting the Sharp Star SCA 260 Super Cassegrain at 1600 millimeters, focal length at f5. Oh, that's nice. That is nice. That's a very nice telescope. 1600 millimeters of focal length, f5. Not bad. Very nice. So in our autofocus routine, we're gonna make this parabola here, and the mathematical calculation for the exact center of the lowest spot, that's where the focus is best. So it won't be an exact, like right there, see? So it won't be at the exact spot we measured. These are the discrete measurements we did. Okay? These little triangles. But you can see it's not on one of those triangles. We can't possibly hope to get that exact, right? So we're going to go to best focus position now. Telescope comes in, focuses. You'll watch these stars go to little pinpoints. Okay, here we go. Right now, we can go back and do our 20-second shot here. Now we are zoomed in. We're at 68% on our sensor. And so we'll minimize this. Oh, beautiful colors. False colors, but they're good. Alright. And so now we have about 3 seconds, and then we'll see this planetary nebula a little more focused. Oh yeah, we're getting there. That looks good. The stars look good. So now what will happen is, as time goes on and we acquire more images here, these details will become more evident. So I'll move my dark level just to the left of the peak, which is the average curve for the red, green, and blue. And then early on, what I like to do, first of all, after doing color correction, that'll make our stars more proper, I like to move this level way down to try and get a peek at this. You see that? It has sort of a red ring and then a teal center. This planetary nebula is the result of a star running out of hydrogen, puffing up into a red giant, and over time it starts to oscillate and do what's called a thermal pulse, and that pushes off the outer layers of the star. And as it does so, it makes a somewhat spherical layer around the star of all this material. Hi, Kathy. Thank you. You have a great astronomical new year as well. Thank you so much. That's very sweet. And so when it puffs off those outer layers, it leaves behind a very, very hot core, just a core. And that hot core is usually in a star like this, where you just have a planetary nebula like this, so named because they kind of look like faint planets. You have a white dwarf left behind. And that's the main end state for most stars in the universe, are white dwarfs. So here is that nebula right now. That's looking really pretty. See that? That's cool. And if we zoom in, let's go to 100% here. So it's 100%. We need to let more data come in order for that to be much clearer. But this is a typical, this what you're looking at here, this is the most common end state of a star, a planetary nebula. Now what happens before you make a planetary nebula, you have that red giant, supergiant sometimes, and in that thermal pulse phase, it's puffing off its outer layers. And on those outer layers, generally the temperature is much cooler than the heart of the star, which is tens of millions of degrees Celsius. So in the outer layers, it's only a few thousand degrees Celsius. And that's still, that's cool enough for molecules to form and for dust to form. And so we get dust formed from these things a little bit, and that gets blown out into the interstellar medium, where it then becomes fodder for the next generation of planets and stars elsewhere. Really cool. So this is NGC 7048. Okay, we'll save this with the annotations so that there's a record of it. And if you're wondering where this is, again, go to skytourlive.org and scroll down, and there's a section that says "Take me to cool pictures," and in that section you will see a set of instructions, and you'll be able to get to all these images that we're creating right now. And like I said, that image I just took is probably already on the server. It's probably already up there. Keith Evans, hello. Nice to see you. So yeah, so this is cool. We've got 11 images here. We'll just go to 12 and then move on. At some point, we're going to try and do a measure marathon too. But that's really long. Marianne says, sorry guys. I don't know why she's saying sorry. Because she probably wasn't paying any attention. Sorry guys, was telling Jake all about STLS and all of you amazing folks. So hi, C&D Boy, Daisy and Zoe, American Road Warrior, Mr. Django, and all the others, I'm sure. She can't type very well. She doesn't know how to type. She's one of those. She hunts for the keys. It's really funny to watch. Don't tell her I said that. She's actually very good to SkyTour livestream. Without her and Tara, this would not exist. Okay, so we got 14. I think we'll go to 15 because we need a little bit more. Mr. Django says, like many of us, don't come to her defense. I'm gonna tell you something really weird. No, Marion, I have the utmost respect. When I was in second grade, I had a typing class. It was a pilot program in the Plainville, Connecticut school system, and we actually learned how to type in second grade. And that skill never leaves you. And by the time I was in junior high, okay, 7th grade, I was typing as fast as I could speak. Literally, as fast as I could speak, I was typing. Sometimes I spelled words wrong, but by high school, I slowed down a little and was more thoughtful about what I was writing. And I could still do, quite a few tens of words a minute, because it's just, we had that second grade class. And once you learn that in second grade, it's really, impresses upon you. I think it's something they should do again. That is really something. Okay. I'm still waiting for more. Now, I don't see the white dwarf, and I'm wondering if that's the white dwarf. It does distinctly have a more blue color. And what might happen is that the star might be moving through space, and these were ejected. And maybe it was ejected at a certain spot, and the stars may be moving a little bit. I'll have to look this one up and find out the morphology and history of it. And when I do that, I'll let you know, because that's really cool. Okay. All right, so that's 19. We'll go to 20. I know, I said we go to 15, then 18, then, yeah, I know. I just want to get the right number so I can get a reasonable view of this when I start to process it. There's 20. Okay, so we'll save it. Save it exactly as seen. All right. So that's a little planetary nebula that we saw along the way, which is kind of neat. Death of a star. We saw a star that blew up, the supernova remnant. We see a star that died a slower death. That was the one that our sun will die when it goes finally. That will be a slow death for our sun as well, just like this one. All right, let's go back here now. And I just can't resist. I'm going to have to do this. Well, actually, first things first. I want to make sure this is centered. Let's make sure that's centered. Yeah, close enough. Okay, good. All right. So that's pretty well centered. So what I'm going to do is I will align on that planetary nebula. Up here. I don't think that's it. Where is it? Is that it? That must be it. Yeah. Okay. So I'm going to align on that now. So you'll watch the crosshair go into the middle, and now we'll be perfectly aligned. Okay, now I'm going to move us down to this region right here. Right there. It literally is one of my favorite regions in the sky. This region right here. So let's head there. And you'll see why in a minute. It's a region known as the Cygnus Wall. It's a beautiful region of dark nebula, and it's so crisp and clear that it's astonishing and amazing how it looks. So we're gonna check that out. So it's right here, right? And let's do a 25-second shot. So we've seen a supernova remnant, the explosion of a star that literally destroyed itself and littered the interstellar medium with all of its guts, basically. And it returns all the elements that it made in its stellar furnaces back to the universe, plus it liberated all the ones it was made with. And now we're going to look at what happens when that material makes its way into the interstellar medium and finds its way to make stars and planets. Okay, so that's our planetary nebula right there. So now, in about 10 seconds, we'll see this North American Nebula wall right here. And you're going to see an area where there's lots of molecular clouds, lots of emission nebula, that is an ionized hydrogen. Look at that. Okay, this red is all ionized hydrogen gas. Let me make it just a little bit more pronounced. It's really quite subtle in real life. So let's go to just before here. And now let's just take our mid-level one and just bring it about halfway, a little bit less. That'll brighten this all up. Okay, so now what you're seeing is you're looking at this dark dust in here that's mixed with hydrogen gas. And there are hot stars buried inside this dark nebula. Again, dark stuff in front of a bright nebula. Okay, and in that dark stuff is some very hot stars that are ionizing this hydrogen gas here, that is also mixed with dark dust, because you could see these dark regions of dust interspersed throughout here. Okay, it almost looks 3D, and you can see these very, very delicate gossamer strands of dark material here. These are light years in size, these strands. They're light years. So if you could imagine we were there, I mean, imagine that. Imagine that we were right in here. It'd be like, it'd fill our whole sky. And we wouldn't even know that we're looking through dark dust. You know? And if we're closer, it would of course look much bigger in our sky and be fainter because it's not as concentrated. You know? So this is that location called the wall. We got some beautiful features here. And the interesting thing about this whole area is, right, we saw the supernova remnant. We saw the planetary nebula, which is the supernova is the violent way the stars go. The planetary nebula is the quiet way that stars die. And when they died and they liberate all that material back to the interstellar medium, this is where it goes. It goes into nebulae like this. And within the dark clouds of molecular dust that was created in those outer atmospheres of these big red giants, okay, and also created in the supernova explosions, you're going to have all this rich assortment of materials from the stars that were made in the stars, and also were made when the star was, or sorry, added to the star when the star was made. They were, the star was made with them, and that kind of thing is something that will create a lot of this dark dust, and it sort of migrates around the galaxy, focuses in the disk of the galaxy in the spiral arms, because that's where star death usually occurs. It's violent because that's where the biggest, hottest stars are usually created, are spiral arms. So in this region here, we have planetary formation undoubtedly going on. We have undoubtedly got new stars forming in here. If the James Webb looks here, you'll see new young stars, most likely protostars, that are stars just turning on for the first time. And it'll take billions of years for those stars to, if they have planets, to produce anything that might resemble life, just like here. Of course, we have to remember that we persisted in spite of 5 major extinction events. If we didn't have a single extinction event in our galaxy, and that affected our Earth, then we might be much farther along and look very different perhaps. We look exactly the way we do, with the symmetry left and right that we do, because of the carbon atom, the way it is utilizing DNA, and the way our bodies create energy. In fact, every creature on the planet has DNA. And so DNA is like a template the universe provides to things that are alive. And it seems that life itself is a template created by the universe, because there have been billions upon billions upon billions of life forms that came and went on this planet. And then there's a few billions now that are in existence for this moment in time. Who knows how much longer that'll be? There are species that go extinct all the time, and we're finding new species all the time when we go to places like the deep ocean, because, you know, we're never really in the deep ocean, are we? So this is really coming along nicely. You can see the detail in this up here. Really something. We can zoom in now. Look at that. Wow. Look at those beautiful, like, tentacles of dust. Hello, Tiffany. Tiffany Echoes with us. Tiffany is one of our donors who gives us equipment to give away. And if you go to skytourlive.org and scroll down, you can see a list of all the previous winners. We have only one winner so far that has yet to claim his pair of binoculars, and that's Creamers. Kreemerz. If any of you know Creamers, please contact Creamers and let him know that he has a pair of binoculars that he's won. He left before he could claim them. He probably didn't think he was going to win. Yeah, Calabos is the other half of Tiffany. And Tiffany's the better half, of course. But that's Michael Calabos. And he is the other donor with Tiffany. And together they do some really nice stuff for us. So we'll probably see more giveaways. Yeah, this is beautiful. Let's see if we can enrich that red a little. Yeah, let me do this. That's too much. I'm gonna let it go to what it wants to be. Yeah, as that dark nebula really shows well. And then you can see down here so much additional material. Now, if you think about it, guys, all this dark dust, this is light years and light years of dark dust. Okay? Now, albeit it's not very dense, it's not, you know, the dust is, again, you may only have 30 atoms per sugar cube size of space here, as opposed to like air, which has 10 to the 19th, 10 to the 20th atoms per cubic inch or whatever, per cubic, centimeter. So that said, it's thick, it's depth, it has depth to it, so we can't see through it, and that's what we're seeing here. But it's dense enough that stellar radiation that might ionize hydrogen here may not reach into the heart of these clouds, because there's enough density that the outer parts are affected. The outer parts are affected by the radiant energy hitting them, but the inner parts are protected, so it could be very cold in here, maybe minus 253 Celsius, and absolute zero is minus 273 Celsius. So that's a pretty fascinating cloud we're looking at right there. This kind of looks like a bat. Okay, we're going to go to 20 on this and then move on. Well, while we're here, let's try and sharpen this up a little, get a little, there we go. Ooh, yeah. Yeah. All right, so let's get some. All right. The stars must be outside our range here. Okay, there we go. That's what I thought. I have to zoom out to see them. Yeah. Okay, we're going to call this the Cygnus Wall. And I will show you exactly where that is while we're acquiring a couple more images. Cygnus Wall is right here, and this whole area is called the North American Nebula. And that's where we are, the North American Nebula. See, there's Florida, Gulf of Mexico, right? Then this is the Pelican on the other side. And we're looking, there's where SkyTour live streams telescope is pointing right now. Right there. So we're looking at this little range right here, this little wall. That's the wall right here. And it's got the most incredible detail in it. Oh, man. Okay, we'll save it, the annotation anyway, even though the nebula's not named. That's fair. Goblins with us. And just want to thank Wayne and Kathy again for the donations. That was very kind. Thank you so much, guys. It's folks like, it's the folks that support us, that, they do have a true love of this material, Not that you don't, you others do too, I'm sure. Jose Navarro says, this was my first nebula photo. You take a picture of the wall or the North American nebula. Probably North American nebula, which is a little higher here. It's up above here. This is like Mexico, and the Gulf of Mexico is like right here kind of thing. Here's Florida. So. Okay, we'll save it. Cygnus wall is saved, and now we will save exactly a scene, which is a PNG, a ping file. And just so, if you go to skytourlive.org and go to our online server, this is what you get. This is the exact image that we're saving up there. So you can zoom into it and say, wow, check all that stuff out. That's neat. See all the detail and everything. Make it, a backdrop on your desktop, whatever you like to do. The other thing, too, is if you're interested, it's Christmas coming up, you can go to our Etsy shop over there, SkyTour shop, and you can buy mugs and all kinds of lamps and clocks and underwear and socks and sneakers with photos like this on them that we've taken. And again, everything up there is a photo we've taken. We don't just use generic crap and stick it on a product and say, hey, look, we got a nebula clock. Nope. If we didn't take it, it ain't up there. It's all stuff we've taken. A lot of the travel mugs are really pretty. Those have been very popular. Okay. One last save, and we're done. So, unlike the supernova and the planetary nebula, which are the end states of stars, this is the beginning state of stars. Stars are formed in these clouds, and these clouds come from the supernovae and the planetary nebulae. So it's like a cycle. After the stars live their lives, they return a lot of that material to the interstellar medium in the form of dust, hydrogen gas, from which new stars can be made and new planets can be made. Really, really cool. All right. So we'll say goodnight to the wall. This is probably realistically the last night we can take a picture of the Cygnus wall with this quality, because it's getting close to the northwestern horizon now. All right. Now let's go look here, back out. And now let's do something. Let's go to Measure 39. That's just sitting up here. It's a little cluster. All right. And clusters form in these nebulae. Okay. And when clusters form in these nebulae, what will happen is those nebulae will end up, there it is, these nebulae will end up being dissipated by the cluster because of the hot young stars with their stellar radiation pushing out on the sky, around them and the nebula around them, and cause that hydrogen gas to disperse. Plus they have motions of their own, and through gravitational interactions, they can work with each other and kind of end up ejecting themselves from the location where they were born. And so this is Measure 39. It's a cluster of stars. Now we can look at it like this, all right? But we can, if we do this, you can see kind of what it would look like in your telescope. Maybe a little more like this is what it might look in your telescope. Again, this is live, but let's actually do a live stack of only a 10-second shot for this. All right, and let's go into our live stack, And we'll get rid of the previous image, which will show up the wall. All right, so that's the nebula. And what you're going to see in the next image is the kind of thing that is produced in these types of nebulae. There, a star cluster. There it is. Now let's do this and do this. Okay. Now it's got red in here because it's sitting around other diffusely ionized hydrogen gas, which has got that soft red glow. If you were with us last night, you saw the California Nebula briefly, and that's a diffuse nebula, fairly dense hydrogen. This is low density hydrogen being ionized by hot stars in the region around wherever it is. Some of these stars may be doing that too. Okay, so if we want to see this more like it really is, we can take our black level, go almost to the top right here. Okay, and now you see the stars standing out. To isolate the stars, we can take our black level on the other side of the hump right here, and we'll start to see how the stars get isolated, because only the brightest ones will remain. Okay, so that's a way to view the stars like that. But this is Messier 39. It's a cluster that people often look at in their scopes, their telescopes. And it's an open cluster, OC. Okay. And it'll be up there like that. And we can save it. It's not, doesn't take much. But that's Messier 39. Doesn't take much to see it. Alright. We'll zoom in a little bit. See how we're doing. Yeah, you can see that these clusters look pretty good. And you'll also see clusters that have red stars in them. I'm not sure if the star is in the cluster. I think it may. Oops, that's not true. Sorry. They may have red giants in them because as the stars migrated out of their nebula, millions of years has passed. Okay, and that may be just enough for more massive stars to use up their hydrogen and then go into a red giant phase, which is where they go after they use up their hydrogen. Okay. And so we might see red giants mixed in with some of these clusters. Okay, certainly that's the case with the double cluster, which we'll probably go to a little later. So there's a lot to see in these clusters, and they're little, I look at them as glimmering jewel boxes in the skies. Glimmering jewel boxes, just beautiful. DK 0018, how you doing? Yep. Awesome. Okay. All right, and so now, Hein Cherry, hi there, how are you? Hein Cherry. Ho, 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 hi, Mr. Django. That's funny. Nicely done. Rockstar, what's up, brother? Okay, so let's save this. And save exactly a scene. So there's Messier 39. I know we're going quick, but you know what? This is going to be kind of cool, because if you go up here to skytourlive.org, you'll be able to check these out later and get an idea of what we're looking at. All right, so let's do this now. Let's fit the width. Okay, and now come back to our stellarium. And now let's go up to this guy right here. Here's an example. All right, while we're seeing supernovae, the nebula they produce, and star clusters that are made in them, now we're going to see a nebula that is in the process of lighting up with a young hot star that formed inside of it. And that's this cluster, that's this nebula here. It's a string of dark nebula at the end of which is a little spherical nebula of hydrogen gas that's been illuminated by a star that literally winked on in the middle of it. Okay, and it's right here. So I think we've got a dead center. So I'll show you. This is kind of interesting. Let me do this and see. Yeah, dead center. All right. Okay. So now what we'll do is we'll take a 35-second shot of this because there's a lot of dark nebula to see here. So we'll do that and go into deep sky mode. This is all dark here. And you notice you don't see stars back here. There's no stars in here. It's not because there's no stars there. It's because this is a string of dark nebula against the much more dense stars in the background. It's a beautiful location. And then this is that nebula that lit up from that one star that has formed inside there. And we'll see it right now. Let's get rid of a previous image. Okay, we'll clear this. We'll clear Measure 39. Hey, Fantasy. Cosmic rays here. And there it is. That is beautiful. Now I'll move this over like that. Make it a little more apparent. And I will now color correct to darken up the background a little bit. Okay, so now you're seeing now right here. Here is that string of dark nebula. Now remember when we looked at the North American Nebula, I talked about those little filaments that were light years in length. Well, here is an example of something that is doing the same thing. All right, now I want to go to the Cocoon Nebula. This is called the Cocoon Nebula. And the distance of the Cocoon Nebula is 6,478 light years. So that means that the length of this very thick tentacle of dark dust is massive. It's it goes on and on and on, way off our view. And it actually is a region where this one star has formed in here, and it's emitting enough ultraviolet radiation to ionize the hydrogen gas that is also liberally mixed into this. And look at, you get one spot of light in here caused by that. You can see dark nebula in here. That's dark nebula. That's again in front of the spherical nebula behind it. You know, that's pretty cool. Hey, old school, how's it going? Sure. Okay. All right, there we go. Yeah. So this is a beautiful area. I'm going to do this. I'm going to take this now, Cocoon Nebula, and I'm going to make that the target name. All right. And I'll save the image with annotations so we have a record of this in the directory that you can get to at skytourlive.org. And again, with Christmas coming, guys, don't forget to check out the Etsy store at SkyTour Shop and check all the many products we have. I think you'll be pleasantly surprised how beautiful these things are. All right. We got to let this develop a little while. We've had 5 done here. But we're doing it for 35 seconds because we are trying to capture some of the intricacy in this dark nebula, and we will be successful. But look at all the stars. Here's something to think about. When you look at all these stars, okay, you got to wonder, well, where did they form? Well, they formed in nebulae like this, vast complexes, and then because of their orbital characteristics, they migrated out of them. The gravitational interaction, they migrated out of them and moved on. And let's just pick on a star. Okay, let's pick on that star right there. I don't even know what that star is. But you know something? That star could have planets around it with life. If it has planets around it. You know? So there's a lot of possibilities in the universe. And this particular nebula is just one region, which is now too hot to host life. Okay? It's too hot to host life in this region because in there's too much radiation. Oh yes, Michael Hedrick is asking about shipping in Canada. I had at least one customer buy something from our shop, and she got the first piece, but the second piece was delayed because of a Canadian mail strike. I don't know when they're gonna restart. You didn't have to delete it though, Mike. It's fine. Cosmic Rays running his sea stars. That's cool. Ray, you should try the Cocoon Nebula here. Now, here's something to notice, guys. When you look at this, you see the red of the hydrogen emission, the ionized hydrogen. But you see the blue? See the blue? See the blue, subtle blue around here? You know what that is? Well, remember, this is dark dust. You know, little tiny particles of dust, very, very small, micron-sized dust. Okay? Well, that material is so small that it is somewhat sympathetic to high-frequency light, which is also very small, very, 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 very small wavelengths. Okay? And so, because it's sympathetic to it, it'll absorb it and re-radiate it almost immediately. That's called scattering. So it changes the direction it's going. If it's coming this way, it might absorb it and send it out that way, or this way, or back at you, or into the page. Okay? And so we ended up seeing that the starlight from this star is scattered around the nebula. Okay? Where the hydrogen is dense, it looks the reddest. Where it's light, you just see a faint, subtle red. Okay? Where it's least dense. However, when you have this dense dust and it overwhelms the hydrogen, like right here, then you get a little blue piece, like right there. There's a little blue piece right there. See it right there? Oops, sorry. Right there. That's a little blue piece. That little blue piece, that right there is a little piece of dark dust which overwhelmed the hydrogen in this area. It's denser than the hydrogen, and so the blue shows through. We see that all around the outside of this. We see that around here. This star is scattering its own blue light. Its own blue light is being scattered by the dust around it, because this star is most likely embedded in this entire dark region here, going all the way up there. So this blue is all a product of that scattering process we see. And it's very blue up here. You can see how blue it is up here. This is the same scattering process that we see in our sky. And it has a name. It's called Rayleigh scattering. I mentioned this yesterday. Rayleigh, Rayleigh scattering. And so it's the reason why we see blue everywhere we look, because those little tiny molecules in our atmosphere absorb a little of that blue light and then re-radiate it, resend it out in all directions. It doesn't stay going in the same direction. The other light coming from the sun is allowed to pass through. So I think that's pretty cool. Neato. Alright, so we've got 13 here. We'll go to 15. Let's go up and see now. Yeah. The cocoon is something. Alright, so from supernovae to planetary nebulae, the sources of the dust and hydrogen gas clouds that we see in the universe, other than initial formation of the universe. And now we're seeing stellar formation. This star right here formed as a result of previous supernovae littering this area of the cosmos with this material. So we're literally watching the chronology of events in the universe unfold by looking at different objects. We saw the clusters. Now, it had more than one star formed in here. They would have had very powerful stellar winds, and they could have dissipated and pushed away all this hydrogen gas, leaving them all alone in space, as happens with many clusters. Also, if they have high motion, then their own gravitational attraction to each other and around the galaxy can speed them around and move them away from their original birthplace. Our sun was born with more than one star. We had more stars in a cluster. There was a time when we thought that we were formed with the Big Dipper stars. And that is no longer true. And if you look at the Big Dipper stars, they're moving in one way and we're moving a whole other way. So clearly we weren't born with them. We're just passing through each other, passing by each other. And so they looked for another star known as a stellar sibling. And they found one. It's in the southern hemisphere where I showed to you. It's a star exactly like our sun, and it has the exact same chemical composition. Why? Because everything in that nebula right there is of roughly the same composition. So if 5 or 6 stars were created in there, they'd all have identical chemical compositions. So the star that we found, the stellar sibling we found, is literally another sun, and it has the exact same spectrum as our sun. It's really quite astonishing. Michael Hedrick asks, Mark, do we know what creates the huge voids in between us and the great attractor? Yes and no. Okay, and I'll tell you why. We understand in between galaxies, okay, first of all, the great attractor, it's a region that everything in our sky there, as we can see it, is sort of heading for. It's a distant point that everything seems to be converging toward. Why? Don't know. We're trying to figure all that out. However, so his question asking about what creates the huge voids in between us and the great attractor. Well, the huge voids are the result, if you looked at the maps of the universe that are available, you can see these huge, it almost looks like a network, a computer network. They're all interconnected strings of material between galaxies. And so where you have a concentration of strings, it makes sense that outside of those, you'll have less of something, less strings. So we see a focus and a concentration, and outside that, not much of anything. So I think it's just the, I think it's just the natural way of things in the universe to develop. Voids are common, in the universe. And so they're the result of very, very large gravitational interactions and the clumping that occurs in the universe between objects, galaxies, clusters of galaxies, strings of clusters of galaxies. And so that necessarily leaves other areas without much in it. Boy, I'd hate to live in one of those things, like one void. Because you look outside and think, there's a star, there's another star, and that's it. Okay. I observed the 2 stars. I observed our universe tonight. For both stars. Notice the detail up here now showing up. You see this little dark band of material that's sitting in front of the subtle blue behind it. And these are beautiful. Let's zoom in on that. Oh, look at that. That's really pretty. The Cocoon Nebula. We love that. Let's see if I can do some enhancement here. Yes, subtle. Wow. And you can see the little patches of blue now here, up here. Oh yeah, Michael, he says it's wild how big the voids can actually be. Yeah, they can be billions of light years in size. Because if you look at the map of our universe, like I said, look it up, and you'll see it looks like a fibrous network, all right, of like a computer network, which is kind of interesting. that we created computer networks that kind of look like the map of the universe without ever knowing what the map of the universe looked like. Neat, huh? Excellent. Do we know relatively how much percentage is void? Okay, from what we can see in the universe, we can come up with a number. However, you have to understand, we can only ever see out about 13.4 to 5 billion light years. That's the limit of our cosmic microwave background there that we see. However, you got to remember that the universe has been expanding. So what we're seeing occurred, 13.8 billion years ago when the universe basically formed. But in that time, it takes another 13.8 billion years for that light there to get to us from there. And during that time, it's expanded even further. So when you take into account that continued expansion that went on the whole time the light was getting here from there, and then you take into account the fact that the universe is accelerating in its expansion, the calculation now to the true diameter of the universe, the true diameter is just over 92 billion light years in diameter. Isn't that crazy? But that's what the science is telling us based on expansion rates, about 92 billion light years. Crazy. Indeed. Alright, well, we're going to save this one now. Yeah, I know Mike Hedrick's trying to come up with some percentages. Not going to be easy, Mike. And I'll tell you one of the main reasons is because human beings can't comprehend high numbers. They just can't. In my book, The Populated Universe, I talk about that. Chapter 1 is called The Problem with the Numbers. And it talks about when we're little, our universe is the crib we're sitting in. And we look through the bars into what would be outer space to us. Wow, the room around this crib. I want to go there. And finally, when you're old enough to actually crawl out of the crib, and now you're in the room. You're in space. Then you go to the window and look out. Wow, there's more to this universe. Not just this room. There's an outside. There's there. And I'm here. I want to go there. So as you get older, you then get to go outside. And you might be in a playpen or a fenced-in yard. And that's your universe. Your universe has grown exponentially from your crib. The 18 by 36 crib. And then, as you get older, you get a bicycle. And you get to ride it around your street. Oh, your universe has just expanded even more. Holy cow. Now, the next town over is the distant universe to you at that point. And the town you're in and the bike trails you've gone down incessantly are old hat. It's just now everything you understand and you accept. But a toddler in his house looking out of his window is thinking, I want to be like him someday. Well, see, we're the toddlers looking out of our window right now, and there's certainly more advanced species out there that are in the towns next to us and then the towns beyond that, and in different states altogether relative to our development. So that's kind of the approach I take in the book to kind of show that, And so thinking about that, it's really fascinating to consider that just trying to make a model of the universe in your ever-growing universe around you, literally you reach astronomical numbers just making a model of the universe. Trying to make a model, I wrote some software, I wrote some programs that I use now and then to figure out, for instance, how to, say, fit the entire solar system in a football field. What's the size of the model? How far is the sun and the earth in that scale? If Pluto's at the other end of the baseball field, the football field, you have the sun right at the touchdown line on the opposite side. How far is the earth? The earth is just a few inches away from the sun at that scale. And Pluto's all the way at the other end of the football field. So, and of course, you make the sun a certain size and so forth. So it's cool to do those mental processes, because then you can actually scale the universe in your mind and go to get a good idea what 40 light years looks like when you're looking at it in the sky. If you know this is 6,400 light years away, then you can figure from having done it before that, we're looking at, here, this has got to be like 60 light years. This might be say, at 6,400 light years. This guy right here is probably going to be 50, 60 light years in diameter, maybe a little less. And this is going to be probably 150 or more light years long, just as a ballpark. So a lot of interesting stuff you can go through when you see this, and then you realize just how big the universe is. All right, I'm going to save this now, exactly as seen. We'll stop here with this one and move on. I'm going to roll, baby. All right, let's get out of this. And let's quit this and go into our low light mode. And once we're in low light mode, we can take ourselves to the next object. So that's the Cocoon Nebula. So named because the stars in the Cocoon Nebula, the star in the Cocoon Nebula, is encased in this dark nebula that is now glowing because it's one star. Okay, the next place we're going to go is another stellar nursery on our way up toward the pole, and that's called the Elephant's Trunk Nebula. This is really cool. By the way, hello, Alicia. Okay, the Elephant's Trunk is a neat location, and it's right about here. And I'll bring this down so we can see it and over. We're kind of close. All right, I recognize those two stars. I know those two stars. They're good guys. So we're going to do this. Can I bring it down? Okay, and then we're going to move to the west just a little bit. Maybe pop it up just a just a tad. Okay, like that. And I'm moving it that way because we're going to see two stars in the middle of the elephant's trunk head doing something I talked to you about, clearing out the space, creating what's called a cavity. And then we'll see a bunch of dark nebula over here that, again, molecular clouds of material and molecular cloud complex. So this will be a 25-second photo of one of the most astonishing regions in the sky. And we'll go into our our deep sky mode. And those two stars right there are going to be the ones we're going to look at. So we're going to clear this out of the way. I think it's pretty cool that we can start at 9 o'clock now. And that way more people can come in and it's not too late for those on the East Coast watching. Okay, here we are. Right, so let me move this. Let me actually do it this way. Yeah, beautiful. Okay, check it out. All right, so let me zoom in here, make sure that we have good focus on these stars. These should be tiny little dots, and they are. So here you see a dark nebula here, okay? This dark nebula, okay, that we're looking at right here. This is all dark nebula, but there's hydrogen gas mixed in with it. So hot stars in the region. Let me see if we can find the hot stars. Okay, stars like this. This is young hot stars, and this cluster of stars here, they are causing this relatively low density hydrogen gas to ionize and therefore glow red. because when you get an ionized hydrogen region, it glows red. It has to do with the electron jumping off, absorbing energy off the atom, and then when it cascades back into the atom, it gives off light as it gives up energy to do so, as it gives up energy to come back in. And that energy being given off is a characteristic color, and they're called atomic transitions. And the hydrogen atoms transition to the second level, n equals 2, is hydrogen alpha, or this red color. Okay, so if you notice in the end here, you see this little round piece. This is what gives rise to the label the elephant's trunk, because here's the trunk. Okay, and here's the end of the trunk. And inside this opening, you see it's like an opening, and there's a star in here. Okay, that star formed in here. And it's a hot star, and it's radiating out with enough stellar wind that it cleared an opening. It cleared away the dust and gas in here. This is just what I told you about, with how clusters of hot young stars can move all the gas they formed in. In other words, once they're formed, they eliminate their nursery. Okay? And that's kind of what's going on there. In Belgium, Mr. Django says, it's 3 a.m. here. Yeah, sorry about that. Ed Gazzaro, how are you? Yeah, you're right. I run a more mellow stream, so I prefer to actually have music that is mellow and lets people, listen and understand what I'm saying. If this is your first time here, by the way, Ed, I recommend you subscribe. It's free. Okay, let me just bring this stuff out. Look at that. Holy cow. Yeah. And go explore SkyTourLive.org so you can see what we're all about. We have a Patreon. We take donations as a nonprofit. You don't have to do any of those things. You can keep enjoying the images. You can download this very image when we start saving them. You can download this very image for free, the one you see right on the screen. So if we annotate this, show you what we're looking at. Okay, we are looking at the elephant's trunk. This is the name of the nebula. Okay, and that is the cluster, the elephant's trunk cluster and nebula right here. So there's the hot cluster that is illuminating all this with its hot ultraviolet energy. Okay, so we'll make that the target name. Okay, we'll save it, save the annotation, so now this image will be saved so you can see exactly what it is, where it is, and so forth. Okay, so this region right here, this deep, rich, God, this is so beautiful. I mean, we're missing this with the last camera. Holy cow. Oh, man. We're just missing a lot of this. This is beautiful. So, yeah, so anyway, this thing here, right, is this star in here has cleared this, all right? And that's what we see again. We see that with young stars. They tend to create cavities around them from the stellar nebula in which they form, okay? You'll notice this has some real interesting structure in here. The elephant's trunk itself, all right? This section over here, this little Humpty Dump thing, okay, this feature in 3 dimensions, we don't really know what it looks like. Some of that's coming toward us, some of it's going away from us. It's not in 2D. It's a 3-dimensional solid object. But this stuff here, this has a name too. This is called the caravan. It's a colloquial name, as is this, the elephant's trunk. In fact, what this is something else. It's called a stalk or a pillar. And when we look at like the pillars of creation, we see that hot stars will strike the dust and so forth and the gas, and around the areas that aren't so dense, it clears and pushes it away, but the dense areas remain behind and then protect what's behind it. That's kind of what we're seeing here with these stalks. Notice this is a stalk too, a little stubbier one, but it's a stalk. And then this was one too, and they're pointing back this way toward this cluster in here. So these hot stars right here are the source for this stalk making. Then over here, we have a similar thing. We have a dark nebula up here, a molecular cloud. And if you notice, in this molecular cloud, there's a lot of detail. This material, it's pointy, and it's pointy because, again, there's a star down here, a hot young star, trying to evaporate it and push it away with its stellar winds. But this area here is dense. It could be that there's a star forming in here, or there is a star and a planetary system forming in here. And so we don't get to see that. But if the James Webb was to look at this, we probably would. And that's what's really cool about the universe. We see only at a surface level like this. This is the visible light view of this area. But only at that level we see it at the surface. But you have to look in the far infrared to see what's behind. Let me make this a little brighter. Bring out some more detail. Okay, there. Yeah. And then let's darken up the background. You come just as shy of the peak and it'll be as dark as you can get without losing data. So we come in here now and we can see this again. The elephant's trunk now takes on some really interesting characteristics. You can see this really filamentary connector to this other area of the nebula. Again, some of it's being evaporated by hot stars and some isn't. And you can see this beautiful cavity that's formed here. With the funding that hopefully some of you could provide with your helping us out, when we get our telescope into Benson, it'll be on a mountaintop with other professional astronomers. And you already know that I'm a professional astronomer. That's what I got my degree in, what I went to school for. And so that's why when I talk to you about these different objects, I'm speaking from the science and not speaking from opinion. So you're gonna always get I think a good background, if you will, on these objects that we're looking at. So I thought it was funny. I was actually, because I'm the chief photo and video analyst for the Mutual UFO Network, I thought it was funny that I was at a wedding and I got these frantic phone calls saying that Joe Rogan's talking about me. And I didn't hear it, but they did, and they heard that Joe Rogan was talking about this guy, and he put my name out there, and he said that analyzes these UFO photos, and so forth. That's what I do. So I thought that was interesting. So I've got some folks trying to get in touch with him, see if I can get on the show. I want to just bring SkyTour to the world. I think it's important. I don't have an ego. I don't care. As long as somebody does it. Just so cool. Fantasy, thank you for the Patreon post there. Very kind of you, man. Our colors are beautiful and rich. Oh, this is just stunning. Wow. Yeah. Okay, so from supernovae to stars that form in the nebulae to clusters of stars in open clusters that have migrated away from their nebulae because they made cavities like this around their star, around their birthplace, and then moved out or pushed it all away, to birthplaces of other planets and other potential stars like this. It's kind of a cool night because we're actually kind of doing the whole chronology of birth, life, and death, so to speak, in the universe. Yeah, Karen Belmont said, I just came in from shoveling snow. Now, I think she's up there in Minnesota, eh? And she just won a pair of our binoculars. She's one of our past winners. Courtesy of Tiffany Echo, 2 comments above her. Yep. Okay, we'll go to 25 on this and move on. Look at this string of dark nebula. This is all molecules of dark dust, mostly carbon molecules and silicon molecules. Really just incredible regions. Again, light years long. And you may remember I talked about this when we looked at the Pleiades. We look at the Pleiades and we see dust around the Pleiades. Well, it could be that that same dust that the Pleiades exist in is the dust cloud that we're in. And it's some research which indicates we might be in the same dust cloud as the Pleiades. And that's pretty cool. All right. So we'll leave behind the elephant's trunk for now. But it's not gone. It's up here at skytourlive.org under the Take Me to Cool Pictures section. Alright, and let's go a little further up. Let's go to the swimming alligator cluster. Again, something I have looked at with this telescope. But we're getting there. Now, why are clusters called the swimming alligator and all these? Well, those are colloquial names. But this is it right here. And we'll take some images of it. Now, you see how many stars are in the area here? Okay. That's pretty cool. But I'm going to show you something. Let's do this. Okay, there it is. NGC 7160. Okay, otherwise known as the swimming alligator cluster. Let me actually... There, it's better. Get the alignment done. Alright, cool. And so, the swimming alligator cluster is, let's see how close we are. Oh, right near the center. That's good. Okay. So let's go look at, let's go here. Zoom in to the center. And we're actually pretty well lined right up on it. Good. Okay. So let's do a quick 15-second photo of this. Alright, and we're going to go into our live stack. Come back to this for a second and clear it. Alright, rejoin our, oh, I didn't want to do that one, I want to do this. That's what I wanted. Okay. And so NGC 7160 open cluster, set that as the target name. Okay, now let's go do some processing to bring all this detail out. Okay, and okay. Nice. You'll notice some diffuse red nebula throughout here. There's a lot of hydrogen gas that's ionized out here by other stars, including some in here possibly. This is a good cluster because it really shows you the contrast between the cluster and the fainter stars around it. That just means that the stars are brighter. See that? So they're pretty bright. This star may be in the same cluster but migrating away. For all we know, I'd have to check to see. I don't know. Do we know the name of that star? Hipparchus 107984. Okay. Alright, so that's good. So Hipparchus 107984. Its magnitude 6.7. About the same as these. Alright, so don't know. We'll have to look it up. Once you have those numbers, by the way, Hipparchus is a star catalog. Tycho is a star catalog. Okay. Bright Star Catalog is a star catalog. And, these star catalogs, the SAO, Smithsonian Astrophysical Observatory, is a catalog. Bonner-Dirk Merstrung, the German catalog of stars. I used that one extensively at the university when I got my astronomy degree. And the AAVSO, American Association of Variable Star Observers, AAVSO, observes stars that change brightness rhythmically and routinely, periodically. And that's something very important too to study. And this is going to be, I'm going to add open cluster to this, OC. Okay. All right, so we did 9. We'll do 10 on this. And boom. Save. These beautiful gems, I'm telling you, you could just spend, and I did. I spent years poring over these, looking at them from all manner of different types of telescopes. You know, I've looked at these clusters using my personal telescopes, the professional systems that I did. I mean, I used this darn thing keeps coming up. Okay, sorry about that. So, and it's been up there since I typed the OC for open cluster. Sorry about that. Anyway, that said, there's that cluster. Now let's go back here, back out a little bit. Now from here, let's go take a look, since it's right nearby. Why don't we take a look at, where are we going? I'm going to go to this guy up here. But first, I think I might want to go here. Alright, first things first, I want to bring up another catalog. Deep Sky Object, DSO. We're going to include the Caldwell catalog, Sharpless, and Barnard catalogs, Lynn's Bright Nebula, and Lynn's Dark Nebula catalogs. Okay, and now we have this guy. Let's come down here. This is another beautiful nebula that we're going to spy on, and we're going to see this bright orange star in here as well, which is kind of cool. So let's go there. We got another bright star right there. Okay. Let's get our, there we go. Okay, so let's now do this and bring up our annotation. Okay, Hipparchus 110504. Let's actually take that star, center it in the view. And while we're doing that, we're going to do a search and find, once it gets there, Hipparchus 110504. Okay. $110,504. All right. So that's that star that we're talking about right there. All right. The red one I was telling you about. And this particular star is interesting because, let me first bring back the annotation properly. Okay. Interesting because it's red. Now, that means several things, okay? First of all, it could mean that the star is a normal red dwarf star, of which we have, that's the largest population of stars in the entire universe, is these little M stars. However, it could also be classified as an M star and be one of the largest stars in the universe. The reason is because the classification letter only deals with temperature. So small, low temperature stars can have the same temperature as massive supergiants that have their outer atmospheres so far from the fusion generating center that it's just as cool out there as a tiny little M star. So what differentiates which one they are is what's called the luminosity class, and that's a Roman numeral after the letter. And in this case, this particular star is a K, which means it's orange, and it's a K2. It's a K2 star, and it's a Roman numeral 1 with a little a, that means it's a red supergiant star. So, in all likelihood, this particular star, being this red supergiant, is probably going to go supernova. Okay? And so, this star right here it's really kind of interesting to see this star here. So we'll get out of the annotation for now, and we're going to move over a little bit because we want to take this nebula and bring it in. So I'm going to go here now. Tell it to go there. And it's only going to be like just a few area, just a little bit away. As you'll see, it's going to move to the left. Now, when the stars are dragging out like that, you can see the colors very clearly. Do you notice? That's really interesting. All right, let's zoom in first to make sure our focus is good. Go to the smallest stars. Looks pretty good. Yeah, looks pretty good. All right, so what you don't see in here is this beautiful nebula. All right, and that's something that I would like you to see. So let me come back here for 1 second. Okay, let's go there. Yeah, so we're going to see this beautiful nebula now, which is right here, and you can't see it unless you take a time exposure. Your eye's not capable of seeing it. So we're going to do a 25-second shot. Here we go. And off we go. This is a stellar nursery, a place where stars are being born. They literally are the nurseries of the universe. It's where we came from. It's where every star comes from. There's trillions upon trillions of these nurseries throughout the universe. The Orion Nebula, for instance, stellar nursery. Running Man Nebula just above it, stellar nursery. Horsehead region, stellar nursery. Molecular cloud. The things we're looking at tonight, this here, stellar nursery. Okay. You also notice something interesting about these. I'll tell you in a sec once I get the colors corrected here, get my curves lined up. There we go. And then we're gonna, let's do this, see where it wants to be. Yeah, I figured it's gonna do that. So we're gonna pull this to just before the peak. It's our black level. That gives us the darkest image without losing data. Then we'll take the mid-range and move it back just a little bit. Okay. Okay, so what's interesting here is if we zoom in, and we've only taken 2 photos, so it's going to be a little grainy looking. But look at this. Look at that string right here. Look at that string. Right? You see that? So we have a string of stars right here. See that? Look at that little string of stars right there. Oh, that's weird. And we got another string of stars. We have lots of these strings in here. Like there, like there. Okay. There's a little one. There. Look at that curve. Okay, a curvy string. Alright. So all these it could be that the star formation took place in this nebula along a shock front, where shock front from passing material started a string of events that led to a star formation event in that region, and then another one, and another one, and another one, and another one in a line. That's possible. There's no proof of that. I have no proof of that. It could also be a line of sight coincidence, because we see a lot of that too in the universe. But when you have many stars in a line like that over there, okay, or like this right here, okay, that means something. Look at this squiggle. It comes up and down and up. Okay, so these mean something. You'll notice here this is dark nebula. This is hydrogen emission. But you'll notice a subtle blue tint here. There's some dark dust in here that's actually scattering the blue light from some of the stars in the region. Yeah. Karen, the types of stars that turn into a black hole are the more massive stars that go supernova. I don't think we've ever seen a normal star that's more massive than the sun, but is going to become a white dwarf or a neutron star after a supernova. I don't think we've ever seen, say, a neutron star that gathers more mass and becomes a black hole. Theoretically, it's possible, but I don't think we've ever seen that happen. Typically, if they gain more mass, they usually have a cataclysmic explosion. Here, let's get this now. Alright, so let's get the name of this object. This is one of Lynn's objects. Lynn's Bright Nebula 471. Excuse me. So, LBN 471. And it's an emission nebula. We're going to call it EN, because you may not readily know the name when you look at it. EN means an emission nebula. Okay. So we'll get rid of that right there. We have 10 of these. You can now see subtle details showing up here. How come we're seeing detail after a while? What's going on? Well, what happens is we take one image, and it's kind of, bumpy and noisy. And then we take a second image, align it with the first, stack it on top, and we make an image sandwich like that. The more images we stack on top of each other, and perfect alignment, the better the noise level is. Remember that when we went to like 81 images on the very first object, the Veil Nebula, the Eastern Veil, we got really, really close and you couldn't even see any of the grain. It was very, very hard to see. And here we have 11, and we're already starting to see some grain as we move into 70%. And then we get really far in, and you can start to see the grain really bad. So we have to back out, and what will happen is, if we take enough pictures, then this will become very, very nice and distinct. So it's cool. Alright, let's go back here while this is going on. And we'll back out a little bit. We have all kinds of directions we can go here. Yeah, we do. Let's that's what I want to do. Let's find this. There it is. Yeah. This is called the Garnet Star. It's near the Elephant's Trunk Nebula. We're going to look at that in a minute. Tell you why. I was named in a grant with Las Cumbres Observatories, which are a bunch of observatories around the world, about 20 or so of them. My goal is to try and find exoplanets around certain stars. And one of the stars I'm looking at is called Barnard's Star. It's the second closest star system to us, other than Alpha Centauri. It's about 6 light years away. And Barnard's Star speeds through our sky. Unlike the closer one, Alpha Centauri, Barnard's Star is a very, very high velocity system. So over a period of like 3 months, you can actually see its movement against the background of stars. And we've done that. We've taken pictures of it. And so Barnard's Star, I want to investigate to see if there's any evidence of some planets that may be around it that were unknown. And the other one I'm going to investigate is Mu Cephei. Mu Cephei is a red supergiant star. So its star long since stopped fusing hydrogen into helium, and it's grown into a red giant more than once, actually. This is probably its second time, and it's probably at a location, I gotta check, the asymptotic giant branch, I believe, AGB. And so that particular star is going to be very big as a supergiant. However, if there's planets far enough away from the star, they could have survived this red giant phase, unlike Mercury, Venus, and Earth. If when the sun goes into a supergiant or red giant phase, it'll swell as big enough to capture and eat Mercury and Venus, maybe Earth. So that said, Mu Cephei is massive, and I want to see if there's any planets that survived that state around it, and we'll go see what Mu Cephei looks like in the telescope in a minute. So here is this beautiful region. Look at now how well developed this is. We're going to go to 20 images. You can see dark nebula over here. Let's see if we can do a little more contrast, and let's pull that right to the left of the, and now let's pull this in a little more and see if that does it. Yeah, look at that, huh? I still want to soften that a little bit. Yeah, now you see how much more is in here. Okay, we will save this now. I gotta change that name. I see that I did not type the right letter, and it's gonna complain when I go to save it. No, it won't. Okay, we can save this now. All right, and this is a stellar nursery. All right, again, birthplace of stars. So now we'll go to this garnet star, so you can see a star that is absolutely beautifully red. Okay. All right, so let's head there. This is a real marathon tonight, huh? Okay, so we're there, and we're gonna go with the garnet star. All right, off we go. And you'll see it because it's gonna be a red star coming into view. Can't miss that, can you? Yeah, that's a very bright star. And if we do our identification, that should be registered as the garnet star Arrakis. Not Arrakis from Dune, but Arrakis, E-R-A-K-I-S. Very bright star. Okay, so what we'll do now is just take a quick 10-second series of shots of this, just to have our record of them, and come back to that and do this. So this is the star that I'm going to investigate to see if there's planets around it that may have survived the red giant phase of the star. Okay, let's do this. First of all, I gotta get rid of this. Okay. Do that. Do this. Color correction. So as you can see, look how rich and red that is. Okay. This halo is not orbits of planets. It's actually an artifact from our optical system. Okay. So, Mu Cephei is actually a very interesting star, and there's nothing but death here. I can tell you that. There's no surviving this. Okay, there's no surviving this phase of a star's life, because it's not like you can move to an outer planet in the solar system, in the star system there, and survive, because this phase is short-lived. So pretty cool. Yeah. Okay. Down here is the Elephant's Trunk Nebula that we looked at earlier. Okay. Alright, this is again just Mu Cephei. We're gonna we've only got, I think, about 8 shots. We're gonna do 10 and then be done with it. a sit stand desk. I gotta convert this to a sit stand. Okay, 10. Save it. Musifi. Alright. So now you see the star that I'm going to hunt for planets on. Around. Okay, now let's go back and look at something else. Amazing. Okay, just scroll out a little bit, a little tiny bit. There we go. And we come back here to our planetarium view. We've seen all this already. Now let's go and let's change gears and move over here now. Let's go to the Broken Heart cluster. On the other side, you watch the telescope swing to the opposite side of the pole. The pole is out there, and there goes the telescope. It's leaning backwards. There it is, heading to the other side. Alright, let's see if we caught it or we didn't. Okay, we got the Hipparchus star, so that's good. That'll give us our star that we can align on. Okay, so this will pull down the center, and that's Hipparchus star. Oh, there's the open cluster. Right there. I think that's it. Let's go see. Oh yeah. Okay, good. So that's it. All right. So let's go to 2281 and center that in the view. That's our goal. So let's do it. Bring that down here. There we are. Alright, we'll set that as the target. So, one thing you should notice right away is that these star clusters are usually all different. They look all different from each other, you know? And that's due to gravitational interactions after formation. They're being tugged and pulled on by each other. And to figure out where the motions are going in these types of clusters, you have to do what's called an N, as in November, N-body equation solution. You have to do an N-body solution, okay, where there's any number of bodies. So N is the number of bodies solution. And it's very complex. To do interactions between two things is okay. 3 things, it gets harder. 4 things, much harder. And when you have an unlimited number, you literally need to have some supercomputing power in order to figure that out. Or an AMD Ryzen 5, like I've got, which is actually a simple system. It's the computing power is well within all of our reach right now. Okay, so we'll do another 10-second shot here. And this again is NGC 2281. It's an open cluster. Open cluster, there we go. And we'll go into our live stack here. Yep, once again, I typed a capital O and that happens. Alright, so let's color correct for any color discrepancy. And now we have this beautiful cluster. Nice. And we can make the background more black. Ex-lady Kathy says winter solstice in Erie, Pennsylvania, December 21st, 2024 at 4:20 a.m. Eastern Standard Time. That's so cool. Yeah, so what's interesting about that is my oldest son was born on the winter solstice, December 21st. Very cool. Okay, so there we go. Look at that cluster. Let's zoom in on that a little. That's neat. Again, this is why we look at these little jewel boxes in the sky. They're just gorgeous. Cosmic Flow 888 says, I could look at the stars all night long. Well, if we do our Messier marathon, we're going to look at all of the Messier objects in one night. And that means that we're going to be up all night looking at them. So you can truly join us and spend the entire night with us if you so choose. Let me just move this up here. Yeah. And there's only a couple times a year when you can do that. And I think you're right, it's April. Fantasy. He said it was April, and I think he's right. Late March, early April. That's when everything is available in the course of one night. Sheldon, I don't know what night we're going to do it. Trust me, it's not pleasant if you've ever done it. What's funny is I did it in a let me just save this. I did it outside, and early in the morning when it's 3 in the morning, the temperature will still reach freezing depending on where you are. So it becomes somewhat unpleasant. You want to get through them all. But we're going to take pictures of them and then have the whole catalog available. Say, here's Measure 1, here's Measure 2. Speaking of Measure 1, we'll go see if we can see that tonight before we end. Okay, so this is that beautiful open cluster over here. This is the cluster that's also known as the Broken Heart cluster. Now, why is the Broken Heart? Well, if you look carefully, you can see a heart. See? There it is. Boop. And here it's broken out. See that? This is supposed to be doing the other connection to make the other line here, but it's broken, see? This side is fine. Comes up, goes around in there, comes out, goes around and down there, no problem. But the point is missing down here, and it sort of picks up over here and then comes back up. So that's why it's called the Broken Heart cluster. You need imagination for these things, but generally people just call it NGC, which stands for New General Catalog, another catalog of objects. New General Catalog 2281, because that makes it easy. All right, 20, save, and save exactly as seen. Done. All right, so we saw that. Now let's go and go back to our low light mode for a moment. Let's dig into something else. Okay, so when you're doing it in this mode, you can see the stars better. Yeah, so let's now come back here. Let's go see now if we can come over here. First of all, there's Gemini down there. And let's do this cluster right here. It's our first winter cluster coming up. You notice that the telescope is kind of peeking at the edge of the building here. So our eastern horizon does have a limit. But this is the next star cluster. We're going to pull out a bit and fit the width so you can see what's going on here. Let's see if we caught it. Yeah, I didn't think so. We have to go to, okay, that Hipparchus star. It might be down here. Hold on. That looks familiar. Maybe go this way. All right, well, what I'm gonna do is I'm gonna center Hipparchus 28734, 1 Geminorum in the center, and then I'll go for that. You know, when you go wildly around the sky, sometimes the telescope's alignment can be messed up. Okay. All right, that cluster looks familiar. All right, we're probably right nearby. So let's do this. We're going to do 2874. All right, so we're going to search. Sorry, did that wrong. You're going to do a search now. That's the search. All right, now Hipparchus 28. Oh, come on. Yes, 28734. Okay, good. Good thing I looked. 28734. That's 1 Geminorum. Good. All right. And we're outside the box. That's good. And we're going to just go there. A line on that. Because that's in the center of our view. And I wonder if we're going to go there too. Oh, the monkey head is cool. All right. Let's first go to this star cluster right here. Everything's upside down. Sorry, so now we're going to see a very bright star cluster come into view. There it is. All right. And when we do this, you'll see a big circle around it. Okay. It's known as NGC 2168, but more affectionately known as Measure 35. Okay, so we'll set the target name. And then we'll get out. Now you'll also notice there's another cluster right here. Okay, this cluster is much further away, and because it's further away, its light is going through some dark dust. And what that does is it takes some of the, remember I told you about the dust, it scatters the blue light? So for the same reason we have red sunsets, distant stars seen through dust will look redder as well, because the blue light is scattered between the sun and us when it's on the horizon. Enough atmosphere it passes through to redden it significantly. So if it passes through a lot of dust, it will redden the starlight significantly. And that's exactly what's happened here. Let's zoom in and make sure we have some focused stars. Actually looks okay. All right. So here we go. We're going to do a 20-second shot of this. And I want you to pay attention to this cluster down here specifically. That's the one they're going to look at. So we're going to come out of low light mode, go into deep sky mode right now. Take out the last one if it's there, because it's already been saved. It's up there now on our server. Okay. And now you'll see Measure 35, a real showpiece that you'll see in binoculars or a telescope. And then you'll see this other cluster next to it. Okay, there we are. So let's color correct. All right, and then let's correct this. All right. So now when we look at this, you can see that it's reddened. There's a red cluster here. This is sort of reddened. And that's because of its distance. All right. This cluster might be the same size or so as that one, but much further away. Let's go check it out. Let's go look and go through this. Let me show you what I mean. So zoom in. Okay. So we have this cluster here and this cluster here. Okay. Measure 35 is also called the shoe buckle cluster, which is kind of interesting. And this distance is about 2,700 light years from us. And then we've got this one here. Okay, this cluster is NGC 2158, and its distance is going to be, let me get the distance of it. Where's the distance? All right, its distance. Did I see it? I didn't see it. All right, distance isn't given, but it's farther away, and it's actually more compact because it's farther away. This is closer, so it doesn't look as compact. Okay, but this is the beautiful clusters in Gemini that we've all been trained to look at ever since we were kids. See how this is, as we get more data, this is looking redder and redder. Now it's kind of looking yellow. This looks bright whitish blue even, and this is like yellowish orange. Again, that's interstellar extinction occurring, which is what that process is, and interstellar reddening. All right, extinction causes the stars to look dimmer than they might normally look. Okay, all right, let's see if we have those values. Okay, let's look here. If we go here, looking. It's not giving us any. It's not giving us the details on it, unfortunately, but that's okay. It's one of those things we'd have to look up. Okay. Well, anyway, this is a beautiful pair of clusters right in the sky next to each other. They'll be in the same field of view if you look in a telescope. And depending on your telescope, you might see this and not that. This might look like a globular cluster to you, but it's not. It's a distant open cluster. So we can simulate different telescope size views by sliding this black level in more. Okay, so if you bring it like way down here, all right, you might see just these stars in your eyepiece, you know, and that's sort of like a simulation. If we just say we bring this way down into the noise, okay, you can see how you would just see this and not even know what that is looking through a telescope. But with a good telescope, well, then you'd be able to see this, and you'd see the two clusters are really there. Really pretty. All right, there's 12 of those. We'll save measure 35 and 2158, NGC 2158. Now, I keep saying NGC. The new general catalog is a catalog of over 8,000 objects, galaxies, clusters, and so forth. Yet another catalog of objects that have been created in more modern times. Okay, so let's come out of here and go back to 1 second. Tonight's a kind of a banner night, huh? We're looking at many things quickly. That's kind of cool. And the reason is because it's not even midnight yet for me. So we're doing well. This is also cool. All right, now let me go look at the all sky camera, make sure that we're got clear skies. Yeah, we still do. And Pleiades is high overhead. We have Aldebaran and the Hyades there. Orion's there. Still too low for us to see the Orion Nebula. We'll have to wait. We have what look like might be planes or satellites, high altitude satellites going by. I doubt that. All right, so let's hop out of here and go back here. Okay, now back here, we back out of this, and let's back out even more. Now let's try this. Let's try this. Now, first of all, if we back way out, I think we're gonna be able to do this now. This is one I wanted to do before. Hang on. I really wanted to see this. Oh, I didn't say that. I said the wrong thing. I said the wrong thing. Yeah, I didn't want to say M17. I wanted to say M1. That's better. And then zip. We're going to be back up in the sky. Why is it saying that? It keeps thinking I'm saying that. All right, I want measure 1. Let me do this. Maybe a space. Holy cow! All right, I'll give it its name. Crab. Yeah, it knows it is Crab Nebula. That's funny. Okay, now it's gonna be way up high. Okay, let's see if we can see this. What's the altitude? Give me the altitude. Oh, 55. Yeah, we can see it. Okay, let's go there. Let's see if we can catch it, because the Crab Nebula is a very, very fascinating object that is a remnant of another supernova, kind of like the veil that we looked at with all the fibrous and beautiful gossamer strands. But there it is. But this one's more compact. It's also further away, whereas the veil is 1,500 or so light years away. The Crab is several thousand light years away. So it's going to be more compact. But I want you to notice, again, this is the first time tonight I've imaged this object with this camera. This camera is tuned to this telescope much better. So let's see how the focus is holding up. I see a little bit of potential. I am gonna refocus. So we'll do that because we'll take care of getting the focus out of the way first. Very important to focus a telescope, and you usually should focus it after moving it across the sky like this. All right, so we'll do that. It'll take about 1 minute 30 seconds. So this object we're going to look at then is the interesting because this will have a central star that we'll see called the Crab Pulsar. This is a lighthouse beacon of a neutron star that's spinning so fast with hot spots that as it spins so fast, they sweep right by us and we see it. So it's like every time it goes by, we catch a burst of this energy. Well, it's spinning over 30 times per second. This is a remnant star. A neutron star is about the size of Manhattan Island. Okay, just a few miles in diameter. And they can spin very, very fast, 33 times per second. If something like the size of Manhattan Island spinning 33 times per second, you can imagine that stuff would be, just thrown all off the star, that it would be obliterated, right? Well, not so, because the star is so dense, its gravity so powerful that it holds itself together. And guess what? That's not even the most quickly spinning neutron star there is. Okay, the quickest spinning neutron star there is spins over 715 times per second. And that's not a lie. Okay, you can look it up. That's a very fast moving Manhattan Island. Okay, we got our focus now. Critical focus is achieved. Now our stars are going to be beautiful. So now what we're going to do is we're going to do a 25-second shot of the Crab Nebula. First time ever with this camera, as I said. So out of low light into stack mode, deep sky mode, and we will get rid of the previous one. Oh, look at Measure 35 looks beautiful. Look at that. See, now you can definitely see that yellowish red color now. So you definitely see the further distance that is. And again, that's interstellar reddening. Looking through dust, a lot of the blue light is extracted out of the starlight from the dust that's scattering it. Wow, look at that, guys. That is the Crab Nebula. And we're going to just color correct here. All right. We can start zooming in already because this is going to get better and better. All right. This is actually pretty good. Yeah, it's crazy bright, this one. So this has all these little tendrils as well. Okay. These tendrils are, again, expanding filaments from this explosion. This is expanding. And over the last 100 years, we've been watching this. Okay. We actually have video of it going dink, dink, and getting bigger and bigger and bigger over 100 years. So this is all the guts of a star being spread out to the universe. And it's going to keep going till it mixes. And then gravity will do its part and start pulling the material into other directions. And maybe locally out there, in this particular part of our galaxy where this is, there'll be more star formation as a result of this. Now, one of the theories is that these filaments you see are created by vast strings of electrical charge in these nebulae. You have to understand, this is all plasma we're looking at. What's plasma? Well, you have a hydrogen atom. It has a proton and an electron. Okay, the electron is in a cloud around the nucleus, around the proton. And if you strip that electron through the addition of energy that the electron absorbs, okay, usually ultraviolet energy, then you have just the loose proton running around and the loose electron running around. That's plasma. So if you have a plasma situation, those are charged particles. When a hydrogen atom has got its electron, the +1 charge of the proton is balanced by the -1 charge of the electron. But when you strip the electrons, you've got a bunch of -1 charges and a bunch of +1 charges. They're all running around separately. So this gives rise to electrical currents, potentially, in these nebulae, which could give rise to the creation of these spindle and filamentary structures we see. The colors we see are the result of hydrogen and oxygen. Now, just like other nebula, we see the bluish teal of oxygen. We see the reddish color of hydrogen. How come we always see oxygen and hydrogen in a lot of these nebulae? The reason is because hydrogen is the most popular and most abundant element in the entire universe. Okay? And then you have helium. Okay? And then the next most abundant element is oxygen in the universe, followed by carbon. Okay? So it makes sense that you'd have oxygen as the third most abundant because you see it everywhere you look. And it makes sense that carbon and oxygen would have a vast interpersonal relationship because carbon-based beings like we are rely on oxygen. And so the oxygen in the interstellar medium is very important to the sustaining of life where it may arise. And so oxygen in our atmosphere is why, for instance, we might be getting visited by extraterrestrial life because they see it. They see the oxygen in our atmosphere and they say, hey, life creates oxygen, plankton in our case, okay? and trees. So therefore, and it's not, it's staying there. It's not going away. Oxygen, that's a burst of oxygen from other processes that are non-living, will go away over time and won't be replenished. But oxygen created by life is replenished. And so we have a constant level of oxygen in our atmosphere. And that's kind of cool. That's what anybody can see looking at our world. You know, Carl Sagan, my favorite astronomer, he said, "We are a pale blue dot in the universe." And he's right. We're a pale blue dot. But boy, are we an obvious pale blue dot. You know, they can see us from thousands of light years away, billions of light years away actually, because the first oxygen showed up in our atmosphere over 2 billion years ago. Look at this. All right, now we're going to zoom in now because I'm going to show you this. Look at this. Here's the Crab Nebula in its intricate detail, and that object right in the middle there, that's the Crab pulsar right there. That white dot, that is the pulsar in the middle. That thing is spinning 33 times per second. Okay? You can't tell because it's spinning so fast, so it's, to our eyes, it's a blur, but it's going fast. On high frame rate video cameras, they can actually see the pulsar blinking at us doing this. That's fascinating to look at. So we'll go to 20 with this one to get the details fleshed out. First time I saw this with this camera, and it's looking gorgeous. Oh, yeah. I can see that we also have a minor issue, but it'll be alright. Okay. That's nice. Really good. Alright, let's see if we can enhance this a little more. Let's sharpen it up a little more. Okay, I sharpened up the spindles more. See that? So if we go in a little more, you can see that we have this very convoluted pathing now that we can see. 2 little tiny stars there. That's beautiful. Look at that. Wow. Gorgeous, gorgeous nebula. And by the way, this nebula, right, is going to be even better looking in our Celestron 11 that we're putting in, hopefully, in the Benson area. We have what are called narrowband filters we're putting in it. I have a spectral system going in it, so we'll be able to look at stars and nebula and look at what they're made of, the chemistry of what's making them up, like what's inside a star, what kind of spectra does a star have. We can find this out with our system. It's going to be beautiful. Okay. And then we're going to have a filter like the one I'm using right here in there as well. So we can take regular shots like this, all full color, or narrow band where we do hydrogen alpha, okay, which is the red part. You just get that. Oxygen 3, which is this part here, the blue part, teal part. And then sulfur 2, which is one of the important components in all nebulae like this as well. Kind of another red. And then we can actually create those false color Hubble shots. Karen Belmont says she has Pale Blue Dot by Carl Sagan. That's cool. Alright. So one more here. Look at that beautiful pulsar in the center of it. That's what's left of this star. That tiny little thing. And by the way, that tiny little thing we're looking at is the size of Manhattan Island. And this is thousands of light years away, and we can still see it. That's how bright it is. And hot. It's so hot. Okay, let's actually let's center up the identification, and then let's make that our new target name. All right, and we'll save with annotations. That's done. Now we'll get out of this and we'll save it with 21 shots. Okay, save exactly a scene. That's gorgeous. Supernova. Another supernova. All right, now we're gonna come back. Go into our low light mode and come back to fit the width here. Okay, that's kind of what you see in a telescope. It's really, this is a very low light object. Sam S, yeah, we're gonna do spectroscopy. Kathy Pernisic says, how hot is it? The pulsar is easily at the surface is sending out temperatures of 50,000 Kelvin, okay, which is roughly 50,000 Celsius. It's off by 273 degrees, but at 50,000 it's not a big deal. We're going to look at this cluster right now as the last cluster of the night, I think, because you'll like this one. And you're going to tell me what you think it looks like. There it is. Okay. This is a fun cluster. Now we're going to do a 15-second shot of this. That's all we need. Yeah, Kathy, it's hot. Yeah, so what I'll do now is go into our deep sky mode here and clear out the Crab Nebula that we had in here before. And then we have this. Alright, now check this out. Alright, this cluster of stars is really unique looking, because you can't help but notice something about this cluster. And what is it you notice? Louis Ta, yeah. Louis TA. You would be vaporized. Yes, you would. ST. Yeah. No, Carl Becker, think different. Let me zoom in so you can see a little easier. Okay, what does that cluster look like? Think of a shape. A shape or something else you know. And this shows you, by the way, the randomness of the universe and what it can do. Hey, Stephen Jarrett, I know you missed last night. That's okay. This one's actually better than last night because we're looking at way more things. And it's kind of cool. Almost, Lewis. Lewis says 31. This is actually called the 37 cluster. See the 7? There's a 3. I mean, you can't get a better 3. That looks just like a 3. So it's called the 37 cluster. Isn't it crazy? I didn't want to do this because it might actually say that. Let me see. Oh. Yeah, okay. That's funny. This is called the LE cluster, right? In other ways. Haha. That's funny. It's the 37 cluster. Don't give me that. If it's a LE cluster, it's backwards. Now from the other side, it might look like an LE. I will say this, though. If you were to look at this through different types of telescopes, you wouldn't see a 37. You'd see an LE because we're swapping, we're doing a flip across the vertical axis because our images are reversed. So we flipped. If I didn't do that, this would be an LE cluster. Imagine seeing it from the other side. I'm just going to do the 12 here. 42 cluster, that'd be fun. That'd be really good. Life, the universe, and everything. The 42 cluster. That's cool. Alright. So we'll save that exactly as seen. That's neat. Okay. This has got to be a record number of objects in one show, I'll tell you that. Let's back out to fit our width. Let's go back to here. Now we got the 37 cluster. I was hoping that would be up. And it is. All right. And oh, there's Betelgeuse. Orion is so close yet so far away. So close yet so far away. Can't look at it yet. Jupiter, we can check out if you like, but Jupiter's view is gonna, of course, just be hobbled by the fact that we're a wide field telescope. But you'll see this really bright object just now come in. But we'll see the Galilean moons. Okay, and I'm gonna get rid of this right away. And we'll be able to see the Galilean moons. See, we got 4 satellites. And let's take this down to a 30th of a second at least. Well, I'll do it this way. Let's do 75 milliseconds. Okay. Hey, thanks, Steven Smet, Mr. Django. Yeah, so let's zoom in now. And you'll see the 4 Galilean satellites. A more nice view. Let's now go in here. Let's center up Jupiter and let's zoom in. And the nice thing about Stellarium is that it does a really good job of telling you what the moons are and where they are. So you can see that we have Europa on the left. Actually, let's do it this way. Let me move us to the west a little bit. Like this. Okay. And let's go back to this. Okay. Now, we back out for a minute. That red square, that's our field of view. Okay. So, what happens is if we zoom in on this now, okay, this here, this planet on this side, this planet here, or sorry, moon, that's Io, right? This is Europa. And this is Ganymede, the largest moon in the entire solar system. It's bigger than the planet Mercury. And this is Callisto. This moon here of Jupiter is the closest moon to Jupiter. Europa just looks this way because it's probably on the far side. But it's in an orbit that's farther out. But so they all look closer, but they're not. Remember, it's in 3 dimensions. Okay, pretty cool. And let's actually see if what we see on the face of Jupiter, we should see this band and this band. With the new telescope, we'll be able to see all this stuff in here. This telescope, because it's wide field, we're probably going to see these bands. Let's go look. Let's go see. All right, so let's head back to the east. By the way, there's a myth about the about the moon, when they said, "Oh, the astronauts, when they look up, they didn't see stars. In the images, it's all black. Yeah, that's because the telescope, that is the cameras they were using, were set to take pictures of the lunar surface, which was bright. Okay, just like we're setting to take pictures of the moons and the disk of Jupiter. And all this is black. However, if we were to overexpose it all, we would see other stars in our view. All right, so it's a matter of how the camera settings were. All right, and we're going to see even less now, because here's what I'm going to do. I'm going to actually take down our gain, which is the sensitivity of the sensor, and you'll see this like all but disappear. All right. Okay, so now let's go lower. You can see the moons are gone now. And now let's zoom in and then start bringing back some detail. We're at 150% on our sensor right now. Let's do this now. All right, we can start to see those cloud bands we were talking about. Yeah, look, we got the two main cloud bands on Jupiter. And if we just make it really bright for a moment, we can see the other moons as well. See that? That's cool. We've done inverse stuff as well. This actually, when it's all white, you can see the cloud bands now as these light spots. Dark stuff gets light, light stuff gets dark. Sorry about those if you're viewing on your large screen TVs. I just blew you out. I apologize. Okay, so there's Jupiter. That's about as good as it gets with this particular telescope. We don't have the luxury of seeing things up close and personal like Jupiter, because we're, again, a wide field scope. So Jupiter takes up so little of our sensor. Okay, here's the full frame. Look at that full frame. That's how big Jupiter is. Because our frame is 3 full moons across and 2 full moons tall. You know, so that's quite a lot of space. You know, but we get to see beautiful things, and we can take pictures 25 times faster than typical telescopes. All right, thank you, Starizona and the Hyperstar. Okay, so now let's get our gain back up. 250, and it's gonna blast us out. But as you can see, when you take the photos for everything else, you can see all the stars. So it's not just a black sky. Shelton says, my brain is growing. That's cool, man. That makes me feel good. All right, so let's pop out off of Jupiter and pull out again to something else. Let's see what we can do now. All right, now there's a lot of stuff up in here. There's the Pleiades. We looked at those yesterday. I'm gonna try something. I'm gonna try. First things first. I'm gonna actually go to a known location. Let's go to this star, Menkib. Okay. We're gonna go to Atik, otherwise known as Menkib. Menkib. Okay. We're gonna go there. Because we want to get an exact look at this precious molecular cloud. Carl, thank you, man. That's just wonderful. Holy cow. Thank you, guys. Okay. I'll guess that that's Menkib down here. Let's do this. Do our nearbys. All right. That's a tick, I mean, yes, that's right. Okay, good. All right, so we're going to center a tick right now. All right, center it up. Good night, Carl. Thank you so much. Let's center it up. Yep. Okay. And as we center it up, we'll be able to now come here and center on Menkib. And this is important because we have to be as close and accurate as we can. Now I'm going to make this go here. All right, so now our coordinates are all lined up, and we can go to the Perseus cloud and capture the Perseus cloud. This is a dark cloud region, which is really quite stunning. And it's got a nebula here and everything, which is really pretty. But if I recall, I want to do this. I'm going to move it up a little. Okay, that's too far. That might be okay. Because there's a cloud in here we want to see. I'm going to move to the west a little bit. Because it's down here too that we want to see. This is a molecular cloud. We talked about what supernovas deliver to the interstellar medium, and among them are these molecular clouds. It takes many, many millions of supernovae to deliver this kind of volume of material to the universe. Okay, I think this is where we want to be. Okay, we're going to find out. All right, I think the nebula, the blue nebula here is what we want, but then we have this other nebula down here. It's huge, so we're not going to catch it all. But I'll do a 25-second shot, and I'll do that from here. And then we'll back out, go into our deep sky mode, and remove our last image of the 37 cluster or the LE cluster. And now we'll see our first shot of the Perseus molecular cloud. Okay. All right. Doesn't look like much. Not yet. But it will. Because this is all a cloud in here of dust. And there in here, the stars, blue light is being scattered by the dust that's over here, which is why you see it. Again, this ring is just our artifact of our system. You can already start to see details in this dust right here. See that? It's kind of too soon to do it, but we'll try it. I'll just over process. So you can see that there's going to be more stuff in here. It's a little too soon. But there's a lot going on in this cloud. It's all down here. The brown is the dust. And then you can see the layout of this dust. Very cool. That's cool, Fantasy. Yeah, that was really nice of Carl, huh? Yeah, no, Fantasy, you're more than welcome. This is cool. Second night in a row. I'll probably wait another day or so before I do another one. And then I may start, I'm going to try and start later so that we can actually mess around with Orion and catch some of the really cool things in Orion. That will be really cool. Let's pull this mid-level in to kind of bring out some of this detail in here. And you can see that now that this blue, There's a dark knot of material here that's in the way. And you can see the cloud here, all around here. See that? Let's see if we can separate that a little. Oh yeah, look at that. Isn't it amazing how much stuff is in the universe? Again, this is many light years in size and depth. So what does it take to have that happen? What it takes is millions, if not billions, of supernovae over time to deliver this much dust and material out into this region. Absolutely incredible. Absolutely incredible. Without a doubt. Okay, we got 7 shots taken here. You can see the details showing up here now. Very complex region. This is the only thing that makes it stand out. And you can see this stuff really starting to appear here. Filaments of brown dust starting to appear here. And if we really push this, you can start to see a little bit more about what's hiding in the background there. But we're going to wait for it. Let it come up. This will be the last object for tonight, by the way. But I wanted to take you through the objects that are the real movers and shakers of the universe. From supernovae to the star clusters that form in the debris fields of supernovae, which are now known as stellar nurseries, as you know, with the dark dust and the hydrogen regions. You know about the hydrogen is the most abundant element, and so is oxygen. So we see a lot of red and blue, teal colors in the universe from ionization of these materials. So that's pretty cool. Daisy and Zoe, thank you for coming. It's good to see you. I hope it was Lane still there, or she probably either fell asleep or drifted off. I jangled the last one. You don't give me that. You were supposed to be sleeping. You said you were going to sleep. So, Okay. Again, I want to thank everybody that donated to us in the Super Chats tonight. Please consider going to our Facebook site at skytourlive.org here, and you can click the donate button. Give any amount you want. I'm not going to beg, but, we are going to need money to put this telescope in the second sight so we can do even more than we're doing now for you. See, by color correcting, you get the browns of this dust much more prevalently. Look at that. It's all throughout here. Let me see if I can just tweak it out a little bit more. Yeah, see? Doing image processing brings new word to the term tweaker. I'm a tweaker, but of imagery. I tweak imagery. Okay. The music you're hearing, this is the YouTube galleries of music, but at the beginning and end of our streams, those songs are songs I've written and composed. So that's very different. That's very special music just for SkyTour. So I hope you like that music too. Yeah, the details are coming out really nicely. Well, what I can do, guys, is I can actually kind of just let you all go if you want, and I'll continue to do this. If you want to stick around, that's fine. I'll leave the stream going here. But if you got to run, that's understandable. I know some of you are drifting off. It's just after midnight now. But I really enjoyed having you guys come out tonight. Okay, Michael. Michael says, I'll say goodnight for now. Yeah, very cool. All right, guys. Well, thank you, guys. I think you should all now go to bed. Think about us. Think about what I was asking about, and if you want to go to skytourlive.org, see what we do. Maybe consider, donating. That would be helpful. That's going to help us out, because we would like to put this stuff in. Put this stuff into the new observatory as soon as possible. John Proctor, how you doing, man? Yeah, John. Yeah, one of these days I have to catch you at the beginning instead of at the end. Well, that's okay. John, where are you located, by the way? Because maybe that's influencing this. In the winter months, we can start earlier, and I started tonight at 9 p.m. Eastern time. You're in Delaware. Okay, you're in my time zone. All right. Let's pull this over. Wow. Yeah, there's a lot going on here, man. These molecules are what are going to make up new planets, and the hydrogen gas in here is going to make up new stars. Really cool. Hey, Donald, thank you. Orion, light your lights. Hey, Jethro Tull. Orion, won't you give me a star sign? Orion, get up on the high line. Orion, I feel fine, and I forget the rest of the words. But yeah, that's Jethro Tull. That was actually one of my favorite songs, harsh as it was, you know. It's definitely an influential constellation. My son's middle name is Orion, actually. I named him. It was influential for me, too. So my son's first name is Hunter. His middle name is Orion. His last name, of course, is D'Antonio. My other son is Gabe, and his middle name is Galileo. Astronomers, kids, what can I tell you? Stephen Jarrett, you're welcome. I'm glad you enjoyed tonight. I think that Jethro Tull song relates to, was that on the album North Sea Oil? Is that what it was? Because it was about the roughnecks on the oil rigs and the life they lead, kind of a thing. Yeah. I've been at sea, and in the middle of the ocean, and I can tell you, the stars are a blanket. However, the ocean is not the best place to look at the sky, because in the other horizon you get this salty haze, but the light is pristine from the stars when it's kind of on a cone over your head here. Really, really beautiful. Good night, Judy M. Thank you for coming. Stormwatch, that's right. Thank you. That's right. You're right. Now I remember. Yes, that was. I have Stormwatch actually. Okay. Let's see what our all sky's looking like. Oh, we got some clouds coming in, guys. Okay, that determines one thing, and that is to not ruin this exposure. See, the Perseus cloud is, it's over here. So we got some clouds. So we're probably taking a photo through clouds, which is why it's not fleshing out as quick as I would hope. Yeah, we're getting some clouds. Okay. Well, you know what? It's a good end to the night, I will tell you. Let me, we're going to do this. We're going to say it's this guy. Set the target name. And I'll just save it. Because I gotta wait for the 30th. Okay, 30. All right. And we'll save exactly as seen. Three and a half hours, that seems average. You know, it's not the longest either. I've done 4-hour streams with you guys before. All right. Well, guys, this has been great. Thank you to all who donated in the super chats. Check us out. Check out our store. It's the Etsy store called SkyTour Shop, and I would hope that you guys would right there up in the upper right corner now. See, Etsy store up here. Yeah, check it out. Lots of cool Christmas gifts up there of all kinds of neat stuff. And by the way, if you guys are into pickleball, we have a SkyTour live stream pickleball set up there too now. You can actually buy the rackets with STLS on them and the ball. So that's cool. So check that out too. I just put that up there. Okay, John Proctor says, scroll back to the beginning and enjoy it. Be well. Hey, you too, man. Thank you so much. Good to see you again. And thank you, John. Thank you for all you do to support us as well. That's very, very good of you. All right. We'll talk another time. My butt's hurting in this chair, even though it's a beautiful chair. That's what happens, you know. I gotta stop sitting so much. Okay, guys. I will leave you be and leave you with our ending song. And you enjoy it, and I will see you again next time we do this. So I'll see you later, everybody. Good night, and have a pleasant tomorrow. See you later.
Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. Sky tour in the night so clear, brings the universe nearer. Real-time wonders to see, streaming live for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across the stars beyond the skull. Through the lens, a distant dream, living real like a gleam. Lift your eye up so high, across the stars beyond the Lift your eyes to the skies, universe in all its light. Sky tours bringing the view.